Good morning, everyone. As a part of Power Electronics series lecture, today I am going to deal with three-phase inverters. I am Dr. Anil Kumar Chappa, working as Associate Professor in Department of EEE at Sri Vasavi Engineering College, Tadepalligudem, Andhra Pradesh. So coming to the three-phase inverters. A three-phase inverter is a type of power electronic converter that converts DC power into AC power. Here we talk about three-phase inverter so that the output we have a three phases which is connected to the three-phase load. So basically it is widely used in several applications, mainly used in motor drives, renewable energy systems and power transmission. So coming to three-phase inverter operation, it has the two modes of operation. One is the 180-degree mode of operation and other one is the 120-degree mode of operation. So we will detailedly explain both two operations further. So before going to explain those two operations or two conduction modes, first of all, we should know what are the key specifications of three-phase inverters. So here this table indicates the parameters at the same time. So parameters for 180-degree conduction as well as parameters for 120-degree conduction. So coming to the inverter structure, either 180-degree conduction mode or 120-degree conduction mode, there we are using a 6 power electronic switches with anti-parallel with the 6 diodes. So totally at the same time, so switch conduction time in 180-degree conduction mode is 180 degree. Similarly, switch conduction time for 120-degree conduction mode is 120 degrees. That means each and every switch in 180-degree conduction mode will conduct 180 degrees as well as for 120-degree conduction mode will be 120 degree. So number of switches are turned on at a time in 180-degree conduction mode is 3 switches and 120-degree conduction mode is 2 switches. So output voltage utilization is high in 180-degree conduction mode as well as lower in 120-degree conduction mode. So at the same time, essential three-phase inverter circuits components. So what are the components we are using for three-phase inverters? That's we have to know. So coming to inverter structure, there we are using, already I told you, 6 power switches and 6 anti-parallel diodes. The power switches may be thyristors, MOSFETs or IGBTs. The main function of these switches is perform control switching to generate the three-phase AC output. So coming to the DC input source, we can use either battery or rectified DC supply. So these two are used to provide DC power to the inverter. So production diodes we are using, those are called as a freewheeling diodes or voltage spike production diodes, which are connected anti-parallel to the MOSFET or IGBT or thyristors. So these diodes are used to deliver the three-phase AC to the load when the load is inductive. So that actually when the load is inductive, what is the main issue is, so it can produce the spikes. So for giving the protection to the switches from the voltage spikes and allow the current path in reverse mode, that is from load to source, there the freewheeling diodes are generally used. So coming to the load terminal, so we are talking about here three-phase inverter. So we have a 3 output terminals which are ABC or RYB. So which is to deliver the three-phase AC to the load. So coming to the control circuit, so gate driver circuits for switching sequence. So generally these are used. So the function of these gate driver circuits are control timing and sequence of power switches. So in sequential mannerly, they will give the firing pulses to the switches. Filter components, generally inductors and capacitors are used to reduce the harmonic content. So if you want to reduce the harmonic content, obviously the output waveforms will become smoother and it reduces the EMI also. So these are the essential components. Those are used in three-phase inverters. Coming to the three-phase inverter circuit, the figure 1 represents the three-phase inverter. It contains 6 switches which are T1, T3, T5 as well as T4, T6, T2. At the same time, it has one source, that is the VS, and the load is three-phase load. So coming to as we mentioned, so voltage source we can use as a solar cell, PV cell. At the same time, coming to switches, we can use either IGBT, SCR or MOSFET as a power electronic switches. So coming to the load, we can use a electric drive we can use as a three-phase load. So this is about the power circuit of a three-phase inverter. So now already we discussed, we have a 2 modes of conduction mode. One is the 180-degree conduction mode and other one is the 120-degree conduction mode. First we need to analyze 180-degree conduction mode. So coming to the power circuit, we mentioned here. So two groups of thyristors are there, which are positive group thyristors, which are in upper leg of the inverter circuit, which is named as a T1, T3, T5. Similarly, so lower leg we have again three switches, which are T2, T6, T4. And these three are all called as a negative group thyristors. So overall, when we observe that the three-phase inverter can be formed by using three half-bridge like circuits. So one is T1, T4 is one half-bridge, and T3, T6 is the other half-bridge, as well as the T5, T2 is the another half-bridge. Totally, by connecting three half-bridge legs, the three-phase inverter circuit is formed. So here, so we are divided into three segments, which are segment one. Segment one means, so this first leg, it consisting of two switches, which are T1 and T4. Similarly, segment 2 consisting of again two switches, which are T3 and T6. Segment 3 consisting of two switches, which are T5 and T2. So at any given interval of time, so both switches in the same segment should never be closed. For example, if the T1, T2 are closed at a time, then what happens is the voltage sources get short circuited, so that these switches can easily damaged with this overcurrents or short circuit current. So in the 180-degree connection mode, the driven connection times of each three-phase inverter circuit is preciously 180 degree of the fundamental period. That means in 180 degree connection mode, the thyristor T1 and T3, T5 as well as T4, T6, T2, every individual switch can conduct 180 degrees. Hence, better voltage utilization is offered under three-phase inverter output voltage. This is the advantages of 180 degree connection mode. So now we talk about, so first we give the gate driver signal to the thyristor T1, so that here the entire time interval is divided into, so 0 to 60 degree is one part, similarly 60 to 120, so 120 to 180 degree, so 180 degrees to 240, like that we can divide the entire x-axis time into 60 degrees. So here what happened, already we told you. So first we will give the gate triggering pulse to the thyristor T1, then T1 will be comes to the on state or conduction state. So already we know that the each thyristor will conduct 180 degree. So initially it is the T1 is starts conduction from 0 to 180 degree. Similarly, next we go for the, now I am talking about only the positive group thyristors. Next I am talking about the thyristor T3. So once here one point you need to observe that. So we have totally three switches in the positive group as well as the three switches in the negative group. So total electrical degree is 360 degree. So 360, sorry. 360 degree divided by 3, so that it will give the 120 degree. That means, so first thyristor starts conducting from 0 to 180 degree. The on the same leg, I mean on the same positive group thyristor, the next device is T3. It will starts conducting from 120 degree. So 120 plus again it will conducting 180 degrees. So up to, that means it is starts conducting from 120 plus 180, that will give the 300 degree. So that T3 will be on from 120 degree to 300 degree, and T1 is on from 0 degree to 180 degree. Similarly, so next one is the same leg we have a other third switch is T5. So T5 will be starts from 240 degree to 240 plus 180, that is again comes to the 60 degree, 360 plus 60 or 60 degree, or we can call as a 420 degree also. So in that way, so we can turn on the positive group thyristors from 0 to 420 degree. So next one, coming to the negative group thyristors. Here again we have a four negative group thyristors, which are T4, T6 as well as the T2. So T4 will be starts already we know that. So T1, T4 can never turn on at a time. So that after closing, after connection time of the T1 is closed, then T1 will get started. So that T1 will be started at 180 degree, plus each device we know that will conducting only 180 degree. So that 180 plus 180 up to 360 degree. So T4 will be on. Similarly, from 300 to again 120 degree. So T6 will be on, and from 60 degrees to 240 degree, again T2 will be on. So this is the conduction times of the switches in three-phase inverter. So this particular figure will give the total conduction time for segment 1, segment 2 as well as the segment 3. In segment 1, T1 will start from 0 to 180 and T4 will start from 180 to 240, and again T1 and T4 will be repeated. Similarly in segment 2, T3 will start from 120 up to 300, it will be T3 will be turned on. From 300 to again 120, again T6 will be conducting. So again it is repeating the cycle. Similarly segment 3 also T5, T2, T5, T2, it will also repeating the cycle. So now we observe that, so coming to the one complete cycle, that is from 0 to 360 degree, we observe that, so the first part is 0 to 60 degree, in that the devices 561 are turned on at a time, and from 60 to 120 degree, here 612 are turned on, and similarly from 120 to 180 degree, in this case T1, T2, T3 are turned on. So 180 to 240, 23, T3, T2, T3, T4. Again 240 to 300 degree, T3, T4, T5. From 300 to 360 degree, T4, T5, T6. Like that again the cycle will start repeating. Again it is coming to the first cycle, that is from T5, T6, T1. It was starting. So from this point onwards. So this is the for one cycle conduction times. If you analyze for one cycle, obviously the remaining cycles also repeating. So the first step is, I consider that, so step 1 is from 0 to 60 degree. So as we mentioned in previously, from 0 to 60 degree, the switches 1, 5, 6 switches are turned on. So again, can we redraw the circuit, the same circuit? So when conduction means it is a closed switch, so it is switch 1 is closed here in this part. Switch 1 is closed here, switch 6 is closed here, switch 5 is closed. That means by observing this circuit, so we have a two conduction switches from the positive group, that is 1 and 5 both are positive group thyristors, and here 6 is the negative group thyristors. If you draw the equivalent circuit diagram for this, what happened here, I can start from the supply voltage Vs plus. So next one is, switch one is closed, so that it is closed switch. Next it will go to the point A. So this is the point, common pointer, this is the A, so that this is point is also called as a point. So that Vs plus, again coming to the A, next one is A. So after that, so here the impedances, here we consider as the three-phase load is the balanced load, star connected, so that all impedances are in each phase is equal. So here we represented with the impedance by the Z. So here what happened, here we are connected a Z, so that here the one impedance Z, and we have a neutral point, this is the O point. So here this is the neutral point O. So next one, so it is connected to where, after O it is again go to the B. So in between O and B we have a one point, that is called as this is the point. So this is the point of OB. So O2 I am going to B, and I am coming to B2 switch 6, and then I am going to the negative terminal of the Vs. So that from O, after that I am connecting Z, and it is connected to the negative terminal of the Vs. And one more point is there here, after B again we have a one more phase is connected at the positive group, so that here after O point, so we have a Z, and it is connected to the positive supply of the Vs plus through switch 5. So that this is, here we are connected like this. Sorry. So here we are connected from here to, through the Vs plus. So this is the equivalent circuit diagram for 0 to 60 degree. So that if you observe that this particular diagram, here we can simply note that here this Z and this Z, two Zs are in parallel each other. So what is the equivalent impedance when two impedances are connected in parallel? Z by 2. So here, this total Z can be divided is a Z by 2, as well as here this is the Z. So what is the total impedances from the A to this what is called this B point or Vs minus is, so the total impedance is this Z by 2 is in series with the Z. So the total impedance is Z plus Z by 2. So now I want to calculate this current. simply I equal to Vs by the total impedance, that is I equal to Vs by Z plus Z by 2. So total, if you are calculating this current I will give the 2 by 3 into Vs by Z. Now I want to calculate the line to neutral voltage, that is the voltage in between. So this is, we know that, so A AO is one of the line to neutral voltage, that is also called as a phase voltage. Similarly, VCO is the other phase voltage, and VBO is the other phase voltage. By observing these two are in parallel, so the voltage across VAO as well as the VCO both are equal. So that here, VAO equal to VCO. So we know that, VAO equal to VCO, that is, if you want to find the voltage across this impedance, so the formula is I into Z. Here, I is here, the Z is nothing but the equal impedances of these two, that is nothing but Z by 2. So totally VAO equal to VCO, that is equal to I into Z by 2. So we know that, I into Z by 2 is nothing but I is nothing but 2 by 3 into Vs by Z. If you multiply this I with the Z by 2, you can get, Va0, that is equal to Vc0, that is equal to Vs by 3. Similarly, now I want to calculate the voltage across point 0 and B. This is the point B. This is the point B. Now I want to find the voltage across this particular impedance. If I want to find the voltage across this particular impedance, again we know that, the current is same, I into Z. I is again, 2 by 3 into Vs by Z into Z. That is, we can get as this Z and this Z cancel. Finally, we can get as a 2 into Vs by 3 is the output. So that means, from 0 to 60 degree, this particular inverter can produce, Va0, VC0 as well as the V0B with the magnitudes of Va0 equal to VC0, that is equal to Vs by 3, and V0 B equal to 2 Vs by 3. So these particular magnitudes are help to draw the phase voltages as well as the line voltages of this particular three-phase inverter. In a similar fashion, coming to the step 2. So when we talk about step 2 means the interval between 60 degrees to 120 degree. In this particular interval, from in previously slide I will show the time taken, which switches are turned on here. So in this interval, from the positive group, switch 1 will be conducting, and from the negative group, switches 6 and 2 will be conducting. So that if I draw the equivalent circuit diagram for this is the equivalent circuit diagram. So when we observe this equivalent circuit diagram, A to O you have impedance Z. Similarly, from 0 to B to 0 to C we have two impedances, Z and Z, both are in parallel. So the equivalent impedance should be Z by 2. So then what is the total impedance of the circuit is Z plus Z by 2 is the total impedance of the circuit. Now I want to calculate the I equal to formula. So the current I equal to Vs by the total impedance, that is Vs by this impedance is Z by Z plus 2. If you calculate by using this formula, you can get current I equal to 2 by 3 into Vs by Z. Next, now I want to calculate the line to neutral voltage, nothing but a phase voltage in between V0B, V0C as well as the VA0. So now I want to calculate the voltage between V0B, that is equal to, because these V0B and V0C are both are in parallel path, so that the voltage is same in two cases. So that V0B equal to V0C, that is equal to current into equivalent impedance. Here we know that the equivalent impedance is Z by 2. The current is already we find, that is the I. So when we substitute I into Z by 2, you can get Vs by 3 is the line to neutral voltage, that is nothing but the phase voltage across V0B as well as V0C. In a similar fashion, now I want to calculate the voltage across the A0. So that here again the current I is there flowing through the A0. So if I want to calculate the voltage, what we need to do? You need to multiply this current with this impedance, that is I into Z. If you multiply this, you can get T2 into Vs by 3 as the Va0 voltage. In a similar fashion, for the remaining intervals also, that is from 120 to 180 as well as the 180 degrees to 240 degree, we can find the voltages across the each phase. In a similar mathematical approach can be applied. For example, 120 to 180 degree, what happened? The voltage across the Va0 you can get as a Vs by 3. Similarly, the voltage across the Vb0 also you can get as a Vs by 3. But the voltage across the V0C you can get as a 2 Vs by 3. Similarly, for this interval also from 180 to 240 degree, here also the switches are conducting from the positive group is switch 3 and negative group is 4 and 2. If you draw the equivalent circuit diagram, you can get this diagram like this. In step 4 here, so we have a again three voltages at every interval, so that means we have a three phases. One is the B0, other one is here V0A as well as the V0C. So coming to the VB0, you can get 2Vs by 3, and coming to the V0A, that is equal to V0C, you can get as a Vs by 3 voltage. So in that fashion you can calculate the remaining intervals also, that is 240 to 300 degree as well as 300 to 360 degree. Then you can find the same phase voltages across each phase. Now, so the main thing is here you need to draw the output phase voltages as well as the line voltages for this particular three phase inverter under 180 degree conduction mode. So that here already I told you this is the very important diagram. So we can understand the how we can achieve the output voltages. Here we observe that the time interval is divided into 60 degree. So each and every interval, that is 0 to 60, 60 to 120, 120 to 180, like that. Similarly, so two cycles it has. So 0 to 360 degree one cycle, from here to again 360 degree is the other cycle. That means it is repeating sequentially. So when we observe that, already we discussed from 0 to I'm just giving a recap. So here from 0 to 60 degree what happened here, we observe by observing this particular thing. So you can observe that, so here, so 0 to 60 degree, so here, so thyristors T1, T6, T5 will be conducting, that is 561 devices are turned on. So that here, so already we are getting, so in this particular case, so VA0 we can get as a Vs by 3, and VB0 we can get from the mathematical analysis, that is the, so there we can get as a, so V0B, that is minus 2Vs by 3. Similarly, VC0 as well as the VA0 both are equal. There we can get as a Vs by 3. So I will write this output waveforms for VA0, that is Vs by 3. So for VB0, that is minus 2Vs by 3. And for VC0, here we can get as a again Vs by 3. In a similar fashion, for the second interval, that is the 60 to 120 degree, that is the mode 2 operation. There, so switching devices 6, 1, 2 are turned on at a time. In this case, what happened? In VA0, we can produce the 2Vs by 3 output, and so VB0, we can get the minus Vs by 3 voltage, and similarly, so VC0, we can get the same minus Vs by 3 only. So you can represent those voltages into in this fashion. In a similar fashion, coming to the next interval, that is the 120 degrees to 180 degree mode, here the switches 1, 2, 3 are turned on at a time. That means 1 and 3 switches are belongs to the positive group thyristors, and switch 2 is the belongs to the negative group thyristors. Simply, if you want to remember the positive group and negative group, all odd number switches are called as a positive group thyristors, and all even number of switches are called as a negative group thyristors. So that here 1, 3 are the positive group and 2 is the negative group. So already we discussed about the equivalent diagram. There what happened? So in this particular interval at VA0, so Vs by 3 voltage will be generated. So that's why we can write this thing. So here for VB0, again here also same Vs by 3 can generate, and coming to the VC0, there minus 2 Vs by 3 voltage will generate. So you can write this circuit diagram in this fashion. Next one is similarly for 180 degree to 240 degree operation. There three switches are turned on. In this, switch 2 and switch 4 are the negative group thyristors, and switch 3 is the positive group thyristor. So here the conducting switches are 2, 3 and 4. So here if you want to analyze the same in mathematically, there we can get as in this particular interval, so VA0 as minus Vs by 3, and VB0 as plus 2 Vs by 3, and VC0 as minus Vs by 3. So in this way, so you can derive for complete one cycle, so you can get this stepped waveform as a output of So VA0, VB0, VC0, which are called as a phase voltages. So next I want to derive the line voltages from the phase voltage. So we know that, so if I want to derive the line voltage, that is for example VAB is the line voltage. So VAB is equal to what happened? So VAB is equal to, so VA VA VAB equal to, we know that VA0 minus VB0. So that here we have a, so VA0 as well as the VB0. So if I want to find the line voltage, that is VAB, what we have to do here, you have to, so minus, you have to take minus from VA0, so to the VB0. That is, so for example VA0 we have a VS by 3, and VB0 you have a, so minus 2 VS by 3. So that what happened, VAB is VS by 3 minus of minus 2 VS by 3. So that will give the your VAB. So that if you do that, Vs by 3 minus of minus 2 Vs by 3, that will give the Va. If you draw the, if you do the math like that, you can get the voltage between 0 to 60 degrees Vs. Similarly, from 60 to 120 degree also you can get as a Vs. In a similar fashion, from 60 to from 120 to, so 180 you can get as a 0. Next one is from 180 to 240 you can get as a minus Vs. From 240 to 300 you can get as a, again, so minus Vs. Again from 300 to 360 you can get as a 0 voltage. So in this fashion, so you can calculate the all the three line voltages, which are VAB as well as the VBC as well as the VCA. If you want to calculate the VBC, what we have to do here is you need to take VB0 minus VC0 from the phase voltages, then simply you can find these voltages. So in a fashion we can get the, so line voltages in a similar fashion. So coming to the advantages of the three-phase inverter, under 180-degree connection mode, it has producing higher fundamental output voltage. The 180-degree connection mode results in a higher fundamental output voltage as compared to the 120-degree connection mode. So which is beneficial for application requiring higher output voltage levels. So at the same time, so it has the voltage across the switches for 180-degree mode is lower as compared to the 120-degree mode. So compatibility with high voltage applications. Generally it is used for, it is producing high voltage, so that it is used for the high voltage applications like power transmission, distribution systems, high voltage motor drives, and grid tied systems. So next one, coming to the, so disadvantages of the three-phase 180-degree conduction mode. So here the main problem is it produces the higher harmonic content as compared to the 120-degree mode, as well as the switching losses are high in 180-degree mode of operation. So, and at the same time, the complex control is required for 180-degree mode operation as compared to the 120-degree mode of operation. Because in 180-degree mode of operation, what happened? So after turn off the one switches, immediately other switches will be turned on. So there is no time. But when we come to the 120-degree mode of operation, that is very simple, because there each switch is connecting only 120 degree. So remaining 60 degree is no switch is turned on. So that particular time is so helpful to, so developing the gate control signal, so that, so as compared to 180-degree mode, 120-degree complexity is somewhat less. So thank you very much.